probably have seen this, a variant of this slide, at least a few times in the past. But just a quick summary I updated. This is from the original DOE exascale report. How long ago was that? 8 years ago. So there were some things that didn't quite match where we are today. So I had to make a few edits to get there. But we are, let's say we are in the 2017, 2018 time frame at this point. And we are already looking to build about 150 to 200 petaflop machines in the about a 15 megawatt power range. That's the chart. We have two types of architectures that we are looking to build. One with lots of nodes, but thinner nodes in some sense. Another with fewer nodes, but fatter, lots of processing power inside a node sort of system architectures. So most of these trends are similar. It's not anything unexpected that we have gone to, but when we move to the next generation, the exaflop generation that we are expected to have in 2023, 24 time frame, all of these increase a little bit. Okay, there's a small jump in many of these. Like from the node performance, we have like about 3x increase in node performance. Each node will get about a 3x increase in performance. And the number of nodes, they will also increase about 2x, let's say. The big difference comes in the amount of concurrency. Okay, how many parallel streams of communication or computation do we have? That is expected to grow about a tenfold just to get this threefold increase in performance. Okay, so that's one of the big trends that is going on. Of course, there are other trends with respect to fault tolerance and so on, which I'll not cover in this talk. Okay, so the general trends in system architectures, the number of nodes is growing. It's at a moderate pace. It's about 2x in the next 7-8 years or so. Number of cores or threads in a node is increasing rapidly. Okay, so the amount of concurrency, the amount of parallelism is going to increase rapidly. About 10x is what we are estimating going to the exascale generation. Each core is not increasing in speed. In fact, in some sense, it's rather reducing in speed. It's not actually increasing in speed. The chip logic complexity is decreasing. That's a little debatable. The current trend seems to show that the logic is actually getting simpler on each chip, though some vendors disagree. They want to put more logic still. But that's a little debatable topic. But it's not increasing drastically in some sense. And what does this mean for networks? This talk is about networks after all, but whenever we look at this overall system architecture, any change in the system architecture has an influence on the network. Actually, they have an influence on each other. So from the network's perspective, the first thing we need to know is there are more cores driving the network. If you have 1 million cores driving the network, different network adapters now, we will have 10 million or 1 billion cores driving the network adapters. There's more sharing of the network infrastructure. This is not a technological limitation. This is it's an economic limitation. Because of the cost limitations, you cannot just scale up the network as easily as you scale up the number of cores. So there's a lot more sharing of the network. More cores share the network. More nodes share the network. So we need to figure out a way to deal with the sharing of the network. The aggregate amount of communication from each node, how much data is each node dumping into the network, that's not going to increase too much. There's going to be a little bit increase here and there, but that's not going to increase a lot. But what will change is how the data is given to the network. We no longer, or we are not going to have these large, huge messages that are being dumped onto the network. Instead, because we have this lots of cores, lots of parallelism, the amount of data, each core will dump in a little bit of data on the network. So we have lots and lots of small messages rather than these few large messages that we had in the past. And lastly, a single core will not be able to drive the network. This is true, already true. Okay, so this has been true for at least 5 years now. A single core cannot drive the network fully. The network is too powerful for a single core to drive the network. You need at least 16 cores today. Tomorrow, in the next generation, it might be even more cores to drive the network. Of course, there's a lot of research to try to reduce the number of cores that are required to drive the network, but we'll never go back to a single core being able to drive a network fully. Okay, the amount of parallelism in the network is just too much to be able to do that. Okay, so how does the network overall architecture look like? This is a simplified network architecture. Current networks don't look like this. Okay, this is from 20 years ago. This is how they used to look. But I think it's a good proxy to understand how things might function, functionally how it would be there. So we have a bunch of processors. Okay, I put 2 processors in this picture, and let's say they have a bunch of cores in each processor. We have a memory subsystem somewhere decoupled, and that connection over there, that cloud-like thing over there, is the is a memory controller, the buses and memory controllers. How do we get to the memory subsystem? From that system, we need to get to the network. So we have the I/O bus that takes the data from the memory subsystem, from the processor memory subsystem, down to the network. And finally, the network adapter that is sitting on your node, the network adapter that's sitting on your node, dumps it to outside the node, okay, to the network switch and the topology of the network switches and so on. That's where the data goes. That's the path the data goes in. Similarly, on the receive side, it's the opposite path. Comes through the network switches to the network adapter, back to the processor memory, let's say, memory or cache. We'll talk about that a little bit. And various things happen over here. There are various bottlenecks. The first thing we need to think about is there are processing bottlenecks. When you are sending a message, it's not just the network that is doing the work. The processor, in some sense, is creating the message for you. Okay, so it has to do some work. And it has to be fast enough that it can send messages rapidly onto the network. So it doesn't matter how fast your hardware is if your processor is not able to create these messages fast enough. That's one of the bottlenecks that we have to look at. The second is the I/O interface itself. So when it goes from the memory processor subsystem down to the network adapter, there is a bus, interconnect sort of thing that takes the data to the network adapter. This is typically a PCI Express sort of interconnect that takes it to the network adapter. That has to be faster. That's the second thing. That's a big research topic going on in the industry right now. And the network end host bottlenecks, there is a channel that takes from the network adapter to the switches, something that funnels the data onto the outside the network topology, and that has to be fast enough. And finally, network fabric bottlenecks. These are typically considered to be fast, but the important thing over here is the sharing. Even though they are fast, a lot of network adapters are dumping in data onto the same fabric. So that has to be scalable in some sense. It's fast, but it might not be congestion-free. We need to look at. But there are three important things I want to talk about. The first is the network adapters. How these the piece of hardware that's connected on your node, okay, how that's designed, what that can do and cannot do. The second is the network topology. Once you're outside the node, when you're on the network switches, when the network topology, that's shared infrastructure, how does that work? And the third part, a subtle aspect that many people don't realize, is the interaction between the network and the processor and the memory. Okay, it's a very subtle aspect. It's something that most people tend to ignore, but that has been one of the biggest problems in network communication so far. Okay. All right, first part is the network adapters, the piece of hardware that sits on your node, okay, that you want to send data out through. The first adapters, the first commercial adapters came out in, let's say, 1979. These are the Ethernet adapters, about 10 megabit per second. Before this, there used to be this a network with Xerox and others had created that was a 3 megabit per second network, but that is not commercial in some sense. The first commercial one came out in 1979. That was Ethernet, okay, 10 megabits per second. Then for 14 years, nothing happened. Okay, everyone was like, "Oh, there's a network. I can send data. I can communicate with different processors. That's great." Okay, it sounded like magic at that time, and people were happy with that. There was nothing changed. And 14 years, 1993, then suddenly people woke up and like, "Well, yeah, I can send data, but it's so slow that I can't really use these multiple computers together." Okay, earlier they were only using for sharing occasional documents. That was fine. The 10 megabit network was fine, but really, if you want to couple these systems into one large supercomputer, something that looks like one big computer, you can't really do that with 10 megabits per second. So they introduced fast Ethernet in 1993, which was a huge success. Soon after that, there was gigabit Ethernet 2. People are actually surprised by how soon gigabit Ethernet was released after fast Ethernet, but it took a long time to catch on. Okay, which is why people tend to think that gigabit Ethernet is much later than fast Ethernet. That was 1,000 megabit per second, 1 gigabit per second. Then there were other companies, ATM. There was a company called Miranet, which I don't know how many people have heard of Miranet. Oh, not bad. So this was a big deal, right? Till about 10, 15 years ago, it was a big deal in HPC, and almost about half the supercomputers in the top 500 list were based on MirrorNet and so on. They were all about this 1 gigabit per second mark. Okay, there was a big jump over there. Then things seemed to stall a little bit after that point. The end host network speeds today are much higher than where they were. In fact, the InfiniBand EDR is an example network that is about 100 gigabit per second per network link. Okay, you can have multiple links out there. In fact, several machines that are coming up, the Oak Ridge machine, Livermore machine, and so on, they have multiple of these links going out, so multiple 100 gigabit per second systems. There are several upcoming networks which are expected to increase the speed several fold, 2 or 3 fold on each link. So there's a big bandwidth networks that are coming out. Okay, so in some sense, the end host network bandwidth, okay, how much data can I dump on the network? That's mostly a solved problem in some sense. Okay, how much data can I dump on the network? Okay, network latency is a different issue. So how much data can I dump on the network? That's easy. Okay, if you want more bandwidth, just pay more money, put a new network adapter, you double the bandwidth. Okay, so it's not that much of an issue. Network latency is how much time does it take if I send one bit from one node, from the memory of one node, how much time does it take to go to the other node? Okay, that's the network latency, and that's a really hard problem. Okay, it's limited by physics, not by money or by technology or ideas. Okay, and this is really hard because we have reached a point where we build a large supercomputer which spans a machine room, and the time that it takes light to go from one end of the machine room to the other and come back for the acknowledgement, that itself tends to be a dominating factor. Okay, we are not quite, there is some room, okay, there is some fat trimming that needs to be done, but we are getting really close to that point where we are limited by the speed of light. Okay, so it's not that easy to get out of. There's of course effort to make systems more denser, package them more closely so that this distance, physical distance reduces. But at some point we need to realize that there is only so much the hardware can give us. Okay, we need to start thinking, if your algorithm is relying on the amount of time it takes for my byte to go to the other end and come back, it's time to go back to the whiteboard. Okay, we have to redesign our algorithm if that's what we are limited by. Okay, we cannot expect the hardware to fix that for us. We'll do a little bit, we'll trim some fat here and there, but eventually that will become a limit. But these are just network bandwidth and network latency. There are other things that we need to think about. These don't give the full picture of the network itself. There are things like message rate. How fast can I drop in lots of messages on the network? Okay, because I cannot reduce the latency, but in some sense, sometimes I can hide the latency. Okay, as in if I'm waiting for the data to arrive, I can do something else. Like I can send another message, okay, or I can send a million other messages. At that time, how many messages can I dump into the network becomes important. Congestion becomes important because if I have limited amount of money, which means my network is shared, how do I make sure that all nodes are not beating up on the same network? Okay, things of that sort become more important. But we have to, those can be improved, but network latency is an issue that you need to think about at an algorithmic level. You should think about that. Okay. So this was a picture that I showed. These are past systems, how network architectures looked like. Processors, memory, there's an I/O bus or I/O interconnect for the PCI Express world, network adapter, and network switch. Today's systems are a little different. First of all, there is an integration, better integration. The memory controller, which was decoupled, which was outside the processor, is now integrated into the processor. Okay, so the memory controller, the blue box over there, is now sitting on the processor chip itself. It can talk to the memory. Okay, so each processor in some sense, or each chip can have its own memory subsystem that it's talking to. This is what we have NUMA architectures. This is how the NUMA architectures look like, right? This was primarily developed to improve memory bandwidth. This is not a network solution. This is for memory bandwidth, improve the memory bandwidth. But it helps with network communication also because it allows the processor to deal with the cache protocol a little more easily than it was with a shared everything architecture. And several network I/O technologies exist today, PCI Express, HTX from AMD, and NVIDIA just announced the NVLink can be used for the network adapters also. It's used for GPUs. right now. These are probably the big ones that allow data to go from the processor, from the memory controller, down to the network. But that's current is already old news, right? We want to look at what's coming up in the future. The next generation architecture is going to have even more integration on the chip. Okay, so of course we have all the cores on the processor. We have the memory controller as earlier, but two additional things are being packaged onto the chip. The first is the in-package memory. I think Pete had a slide that showed that for the Knights Landing architecture and various other architectures. They're thinking of having some part of memory on chip. And plus, there is a network interface. The network adapter itself is also being integrated on chip. Okay, so it's becoming more, the chip itself is becoming a hub for all these things to converge, to get into one single place. Okay, and of course, there is some off-chip memory as well, so the network adapter and memory controller have to address both of these. It may improve network bandwidth. I've seen some marketing slides where I see that, oh, this will improve the network bandwidth so much and so on. I don't quite believe that. It's unclear how much network bandwidth improvement that will have. There's a lot of effort in PCI Express and HDX and so on, which are already making sure they are not a bottleneck at all. So that is something to think about. But it will almost certainly improve network latencies. Okay, because when you're forming a packet, when you're forming a message to send over the network, there's a lot of control messages. There's a lot of coordination. There's a lot of setup that is required to actually just create the message. Okay, and that requires a lot of going to memory, back and forth with the memory and processor and so on, and with the network controller. And this integration allows this preparing the message, this setup part of the message to become much faster. And when we are talking about speed of light limitations, the setup time for the message becomes a real bottleneck. And if you can trim some fat over there, that improves the latency. So it can help improve latency quite a bit. But one subtle aspect that people don't realize is the integration with the processor. Earlier, we had a processor, we had the network controller, and they're both talking to memory. But when they're both talking to memory, they're not quite coordinating with each other. Okay. One example is atomic operations. Okay. When a processor does atomic operations on memory, it's doing its atomic operations. The network can do atomic operations on memory as well, which is fine. But when both of these are touching the same memory, they're no longer atomic with respect to each other. Okay. When you have this sort of integration, there is potential to solve these issues by making this coordination a little better. For example, by making atomic operations atomic with respect to CPU and processor. Well, current generations doesn't do that, but there is potential to be able to do that once you have everything on the same package. Okay, because there's better coordination. Okay, all right. So let's talk about the bottlenecks that we referred to a few slides ago. Okay. The first thing is the processing bottlenecks in the traditional protocols. So earlier, we used to use TCP, we use TCP even now on our laptops, but not on supercomputers, right? We used to use TCP or UDP, which were built in a way that are generic to all architectures. Okay, so very portable, work everywhere, but they kind of don't take advantage of all the hardware because they are meant to be generic. They're meant to work everywhere. So they do various things, data buffering, integrity, routing, packetization, creating messages. All that stuff is done in software on the processor. Okay? And the host processor, it's a general purpose processor. There's only so much it can do. Okay? It's not built to make TCP faster. So it's a general purpose processor, and there's so much it can do to try to speed that up. There are hardware solutions to do that, but by far, it's all done in software. And they're signaling different layers and so on. So that essentially was becoming a bottleneck for the processing itself. Today, we have moved to what is called as an offload era, where nowadays, most of the protocol processing is done in hardware on a specialized ASIC that is built for doing the network processing. Okay? It's not done by the host processor anymore. The host processor still has to tell the network adapter to send a message, but most of the work is actually done in ASIC on the network hardware, okay, not on the host processor for almost every supercomputing network technology that exists today. Okay. Reliability, packetization, everything is essentially done in hardware. This is in the traditional side, right? Traditional Ethernet. I don't know if you guys remember the OSI ISO stack, but there are multiple layers of this stack. And different layers are responsible for different things. There is a layer responsible to the flow control, error detection, and so on. There's one responsible for routing. There's another responsible for reliability and an abstraction layer. And above that, other high-level systems like HTTP or FTP or whatever. This was how the original stack looked like. And almost all of that was software, except for the bottom physical layer, which was hardware implemented. Nowadays, the physical layer, of course, is still hardware-based, but the upper layers are building up essentially the same techniques, not identical protocols, but the same concepts, the same ideas. Okay, they're building all this, but the key part is that this is all in hardware. Okay, all this part, the network, the transport layer, network layer, link layer, physical layer, everything is hardware. It's everything put on a single ASIC hardware compressed together. Okay, and a large number of network APIs exist so that an application can use these network adapters. Okay, this protocol, hardware protocol that's available, there's a way to use that through these various network APIs. There are three APIs I'm mentioning over here. The first is the Open Fabrics interface. This is primarily led by Intel and Cisco and various others who are trying to expose a uniform network communication layer for all of their network adapters. There's another thing called Unified Communication X. I don't know what X stands for, maybe Extreme or something. This is primarily by Mellanox, IBM Oak Ridge, and so on. They are trying to do some similar thing. InfiniBand, for example, Mellanox InfiniBand would use this sort of communication layer. And there's a third layer, there's Portals 4. This is by Sandia National Lab. It's unclear if Portals 4 API will still exist or it'll just remain as a hardware specification and get merged into OFI. It's unclear, that is unclear, but for now these three big APIs exist today for network vendors to choose from. So in some sense, the network hardware gives these capabilities. These APIs, these libraries, abstract these capabilities and provide them to you so your application or your MPI library or PGAS library can use the network in a rather simpler way than directly talking to the hardware. When you're using a high-level programming model such as MPI or PGAS, several of these aspects are hidden from you. Okay? You don't actually see these aspects, but in order to understand some of the costs associated, for example, to understand why does MPI do this the way it does, okay? It's good to know what's going on in the network layer. So let me just give you an overview of how communication happens on the network hardware. Okay, then the MPI tutorial can probably connect back to this to say why it did it this way. Okay, so we have the process, the user process. We have the operating system, the kernel over there, and then the network hardware that's sitting. Okay, the process first, before it can do any communication, it has to tell the network hardware what buffer is going to send data from and what buffer it's going to receive data into. It has to tell the network hardware, okay? So the process first tells the operating system, okay, before it does any communication, okay? It hasn't done any communication yet. It tells the operating system, I want to send data from this buffer over there, okay? That's step one. Then the kernel does some work. It essentially translates the virtual address space that the process gave into physical pages. It pins the physical pages. Okay, because now the hardware is going to be directly accessing those pages. So we cannot have the virtual to physical address mapping changing during that time. So it pins the pages. It guarantees that the virtual to physical address translation for those pages don't change. Then the kernel tells the network adapter this mapping. Okay, the network adapter keeps track of this because when the user says send data from this virtual address space, it has to figure out which physical page is the user talking about. Okay, so the network adapter keeps track of that. And then it tells the kernel, OK, I'm done. And the kernel returns to the user process saying, OK, we are all done. Okay, that's the general process. Now, there are optimizations along this way and so on. And sometimes the network adapter has an IOMMU, which does this automatically. But more or less, okay, I made the process a little bit more explicit in this picture. OK, that's what is happening. After this is done, now I can set data from this buffer. Okay, so this is the pre-communication step. I didn't do any communication just yet. Okay, once I'm done with that, now I'm ready to send data. And to do that, now I have this memory, the purple-ish thing is the memory system, the blue bar is the processor, and the network hardware at the bottom. Now, if I want to send data, the first thing I need to do is this memory segments over there on the sender and receiver side. I have to tell the network adapter that I'm going to send data, receive data from, right? After I do that, the receiver tells the network adapter, here is where you need to receive the data into, okay? And the sender tells, here is where you should send the data from. So these yellow things, they are called work queue entries. Other networks call it other things, but more or less the concept still exists. It's basically a data structure that explains where the data should go from or should be received into, okay? And the network adapter hardware takes this data entry. I'm not going to talk about doorbells and so on, which is hardware mechanism so that to tell the hardware. But somehow the network sees this work and sends the data to the receiver side. The receiver side sees the receiving the buffer, the data structure pointing to the buffer, and finally puts the data into the receiving memory segment. And once the data is done, it'll put the entry into a completion queue saying I have completed, because user should know that the data transfer has completed, and sends a hardware acknowledgement back to the sender saying I'm done with the data transfer, and the sender then puts this work queue entry into the completion queue. Okay? So general model is I send the data, all the data transfer is done in hardware, the reliability checks are done in hardware, and I put back a data structure in user space saying I'm done. Okay? Everything else is handled by hardware. That's for traditional send-receive communication. Put-get communication is similar, except that it doesn't involve the receiver processor at all. Okay? And the network hardware takes this data and directly transfers it onto the target destination buffer. Note that the target processor is not involved at all. Okay? There is no instruction issued from the target processor hardware, okay, for a true hard network-based put operation or a get operation, which is the other way around. Okay? And of course, there's the hardware acknowledgement, and the completion happens on the sender side. There's no completion on the receiver side, on the target side, because the target doesn't know that the data got put into its memory. Okay? And last thing is atomic operations. As I said, atomic operations today are only atomic with respect to the network adapter. Okay? If you send two atomic operations to the same network adapter, they will be atomic with respect to each other, but they are not atomic with respect to other entities, such as the processor. Okay? That we need hardware integration for that. We don't have that yet. So atomic operations, again, very much like put. I send the data, but on the target side, the network adapter in hardware does the operation and puts the resultant data to the target side. So you have operations such as compare and swap, or fetch and add, things of that sort that the hardware can do. It cannot do any generic operation, okay, because it's done in hardware. Okay? There are only a few operations that are implemented in hardware. Okay? For everything else, you have to use some software handlers or whatnot, but the hardware can do a select few. Typical adapters give like 2 or 3 hardware operations that you can do. Fetch and add is a common operation because almost everyone uses that. Compare and swap is also another common operation because for things like linked list manipulation, you need compare and swap in hardware. These two are very common. Some network hardware gives things like swap, not compare and swap, but swap, and various others also are implemented in hardware. Protocol capabilities are being offloaded onto the network hardware. As we move forward to the next generation of networks, the network hardware is becoming even more specialized than what it is today. Okay? One example, the Blue Gene architecture is an example of that. The Cray network is another example of that. They're not just offloading communication. They're not just offloading protocol processing on the network adapter, but they're also offloading things like MPI communication, okay, MPI processing on the network adapter, or PGAS processing on the network adapter. Okay, so the portals-based networks such as the Cray C-Star or the Bulls BMI network that's coming up next year, I believe, they are already looking at offloading MPI send-receive matching, for example, on the network hardware directly. Okay, So there is more and more incentive for network adapters to try to offload higher level stacks onto the network adapter. That's one way of improving latency, right? If you do things that traditionally were done in the host processor, if you put them on the network adapter, make them faster, in some sense you are reducing the latency of communication by doing that. So in general, the process is, earlier everything was in software, now almost all of the network processing, protocol processing is in hardware. Going forward, even higher level stacks are being offloaded on hardware, integrated on the network hardware, and so on. Let me quickly go through what happens once the network adapter got the data, it created the message, it tries to send the data out onto the network hardware, outside the node. What happens at that point? So that's where the network topology comes in. Traditional network topologies, years ago, used to be crossbars. Crossbars are essentially all-to-all connections. Okay? If you have a bunch of nodes, a crossbar will essentially give an all-to-all connection between all these bunch of nodes. Okay? As you can imagine, that's fantastic, right? There's no congestion, everything can go through as it wants, but it's also very expensive. Okay? In fact, today you cannot build a crossbar for more than 64 nodes, more than 64 network adapters. Okay, that's the largest crossbar you can build. There are some specialized crossbars that can do 128 or 256 nodes, but they cost a lot of money. Okay, so you can't just keep scaling that to larger systems. The next generation after crossbars came fat trees. Okay, so fat trees are essentially they're somewhat like crossbars. Between any pair of processes, there exists a completely non-blocking path, but not all paths are non-blocking. Okay? So in some sense, if you knew exactly what my global communication is going to be, I can plan this global communication so that I can set up non-blocking paths for all communication. Okay? However, if you give me a random communication, peer-to-peer to process-to-process communication, which is global, I cannot guarantee that all that communication is going to be non-blocking. Okay? That's the difference compared to crossbars. It's cheaper, okay, but the important thing to remember even with fat trees is that the size of the network, the number of network components you use increases with the number of nodes. Okay? So it will scale to some point, but eventually you'll run out of money, right? So you can do this for, let's say, about 5,000, 10,000 nodes. Medium scale clusters, you can use this. But when you build lots of nodes, 100,000 nodes, you might not be able to use the fat tree because of cost limitations. But even the newer systems, some of the newer systems that are coming up, like the Oak Ridge machine and Livermore machine, they are still based on fat tree because the number of nodes they are using is not that high. Okay, it's about 5,000 nodes, so they can still use a fat tree. But when you think about machines like Aurora, which are 50,000 nodes, then you have to rethink whether fat tree is cost effective. Now, of course, there are newer topologies that people are looking at to make it more scalable, because they are not really scalable with respect to performance. They're scalable with respect to cost, okay, or money. They all use torus topologies of various dimensions, various number of dimensions. The new network topologies that are coming out are Dragonfly or Dragonfly Plus networks. These kind of allow more sharing, or force more sharing rather, but all these networks try to focus more on locality. Okay, so you have to be very careful about who is close to me, physically close to me, and who is far away. Okay, because if you screw that up, you are communicating globally over the network, all over the network, and that can be really expensive. Okay, so I have a few graphs with torus, but the aspects with Dragonfly would behave similarly because of the sharing. If you have two pairs of processes communicating and they overlap, in the picture at the bottom over there, P3 to P4 is overlapping, the performance just drops to about half. Okay, because, well, it's shared network link. Okay, as far as you are thinking of it, I have two disjoint set of processes that are communicating, right? P3 is communicating with P4, and P2 is communicating with P5. So they're disjoint set of processes, but inside that communication, there is a network link that is being shared, which means you only get half the bandwidth. So on the left side, I have an algorithmic view. Those are my neighbors. The red dot has those blue dots as the neighbors, okay? And from an algorithm perspective, those are my neighbors, right? They're neighbors. If I map that in the default topology for the blue gene PQ architectures, that's how the topology is going to look like. Those that appear to be neighbors in my stencil computation are no longer my neighbors when I've talked about my hardware physical topology. Okay? Which means a lot of links over there between this communication are going to be shared between this communication. And most programming models allow you some query functionality to do this mapping appropriately for you. MPI, for example, will give you a way to map your application communication graph with the network hardware communication graph, which you should be using. It's particularly important for these quote-unquote scalable networks, which are not scalable with performance. So for those, it becomes particularly important to start looking at close-by processes. Last piece I want to talk about is the network and processor memory interactions. That's a subtle topic that most people tend to ignore. They think that the processor is sending data, the network is magically communicating all this data. There's something that happens with the processor and cache and so on. We need to be aware of that. Most network interfaces are aware of the processor caching model. Okay. They know that and they cooperate with that. You cannot have a network adapter that completely ignores it, otherwise it'll be unusable. There have existed some networks in the past where you have to explicitly manage everything, but it was a nightmare to do that. Most current network adapters, you send data, you send a buffer, and they will figure out that this is in cache, the cache is dirty, whatnot, and they will do the right thing for you. Okay. So let's see how that works. So let's say on the sender side, I have a buffer. Let's say it's sitting in memory, and I want to send the data out. If it's sitting in memory, there's really not a problem. The network adapter goes through the NOT bridge, goes through the memory controller, and accesses the application buffer and sends it out. Okay? There's no problem in doing that. But what happens if the data is in cache? Okay? Now the network adapter, together with the memory controller, figures out that it's in cache and uses that data and sends it down to the network adapter. It also keeps track of the fact that, if you remember your cache coherence protocol architectures, like the messy architecture, it's in the modified state in the messy architecture, it will see that it is modified, it's dirty, so it will also write back a data copy to the memory. The state of your cache, the state of your buffer decides your network performance. Okay? If the cache is dirty, it has extra work to do. The network adapter and the memory controller have extra work to do because they have to send a copy of the data back to memory. And if your memory is slow, it doesn't matter how fast your network adapter is because it still has to move the data back to memory, and that takes time. On the receive side, it gets a little bit more trickier, especially if there is a data that is sitting in cache and it's dirty, whatnot. So in that case, the memory controller has to flush this cache, push the cache back into memory, or invalidate the cache if it's in exclusive mode, and then write the data into the memory system. Okay? The important thing to note is that for the receive side, it's only interacting with the memory in this picture, not with the cache. Okay? That's a slightly older view of how things work. Modern network adapters are looking at something called as a direct cache injection. Okay? On the sender side, I can send data directly from cache if it is in cache. On the receiver side, why can't I directly receive it into cache? Okay? So that's what is called direct cache injection, which several networks are looking at. It's been shown on old networks too. Psychotex, for example, had direct cache injection, which most people didn't realize it did. But you have to be very careful when you think about direct cache injection because the network can go and put it in your last level cache. But if you don't use the data immediately, you're polluting your cache. Okay? So you have to be very careful. It's a double-edged sword. You have to be careful how you use that. The other thing is the atomic operations. I think I pointed this out. It's very hard for the network to be able to do atomic operations, or even for two network adapters to be atomic with respect to each other. It's very hard to do that unless you talk about integration of the network adapter onto the processor chip, in which case it can theoretically become easier, though that's left to be seen whether that will happen or not. So we saw a big increase in performance going from petascale generation. We are looking forward to the exascale generation now. And the networks are playing a big role. But the important thing is every time there's a 10x increase in performance, something breaks. Okay? And we are talking about a 1000x increase in performance going from petascale to exascale. So we already went through a few breakages, and we are going to have some breakages in the way the network architectures look like as well. One simple example is the network processor integration on the same chip, but there are other sorts of breakages as well, as more protocol hardware stack being offloaded onto the network and so on. But there's a lot of work to be done on the network. There are some things the network hardware can fix for you and is fixing for you. There's some things it cannot fix, like network latency, which you have to go back to the whiteboard and start drawing your new algorithm of how you will avoid network latency hits and so on. But interesting times for all architectures, and whenever there's a changing of an architecture, it affects everything. So interesting times for networks as well. Thank you very much, and happy to take questions.
Talk about the direct cache injection method, and you are saying I'm sending from the cache, I'm receiving from cache. But is that, if you're doing one-sided communication, if you're receiving from cache, how can you not involve inside this receive processor, for example, because you're putting it in the chip, no?
Well, for one-sided communication, if the memory is on package, whether you put on memory or on cache, you're putting on chip anyway. Okay. What I mean by processor is not involved is that there's no instruction issued on the target side.
So if you put in the cache, you can also don't issue any instruction.
That's correct. That's correct. On the last level cache, though, you can put it on the last level cache without any processor interjection, without any instruction being issued. But for one-sided communication, it's trickier because the target does not know that the data has come in. Okay, so putting it in a cache might be a bad idea, because if the target doesn't know the data has come in, it'll probably not use it immediately. Right. So you just polluted the cache, and the target cannot use it. Okay, so you have to be careful with respect to how you use the cache. Is a limited resource. If the network is dumping data in that, if you don't use it immediately, it's a bad idea.
So if we are using MCD RAM, which looks like a cache, is that the better idea, because we have?
If you have on-package memory, okay, MCD-RAM, IPM, whatever you call it, right? If you have on-package memory, there are two ways you can use on-package memory. One way is you can use it as cache. Okay, it's completely hardware managed, everything, right? Another way is you can use it as a separate piece of memory that you can directly access, right? You have actual virtual addresses for that memory, or physical addresses for that memory, right? I'm talking about either way you use it. If you put it as regular memory, it's no different from the network hardware is just putting in memory. It just happens to be on chip. If you use it as cache, you can still put it with direct cache injection. You can still put it in that cache, but you have to be algorithmically, you have to be careful to use your cache in the most optimal manner. You don't pollute it unless you want to use it immediately. Okay?
And another thing is about the mapping you said between the file, the stencils to the network topology. I'm not understanding that picture. Yeah.
So in a stencil computation, right? Suppose you don't use any topology query mechanisms. Okay. Suppose you don't do any of that, and you say I have 100 processes. Okay. I will distribute it as a 10 by 10 grid, and I will decide that rank -1 and rank +1 are my neighbors, and rank -10 and rank +10 are my neighbors. Okay, let's say I decide that. From me, intuitively, from an algorithmic perspective, without knowing anything about the hardware, it looks like they are my neighbors, right? Up, down, left, right, right? Because I viewed them as a grid. But my point is, if you don't query the network topology, what you view as your neighbors in this algorithm might not actually be real neighbors on the network hardware.
Are you saying when you are mapping a high-dimensional problem on a low-dimensional network topology?
Could be a different dimension mapping, but in some cases it's exactly the same dimension. Even then, your mapping gets messed up. Maybe I can draw on a piece of paper for you after this thing. Yes?
Regarding the send-receive diagram that you showed, that involves the OS, and typical communication would take place at some granularity, like a page. So going forward, if future systems are sending out a lot of small messages, that page granularity becomes a bottleneck. That means while designing the algorithm, do I have to take that into consideration, and how to do that?
So first of all, the communication itself does not involve the OS. It's all user space going directly to the network hardware.
Since it goes through the OS, I mean, the OS would pin pages into memory. And
so that is the pre-communication step, right? So you are registering your buffers and going to the network adapter and so on. So you're absolutely right. If you have lots of small messages that are random, you might be hitting different physical pages. Okay, and the network adapter usually has a small cache with respect to your virtual address to physical address mapping. Okay, and if you are touching multiple pages at the same time, you will run out of this cache, and the network adapter has to go to memory to get the rest of the translation and so on. So it will hit performance. You are absolutely right about that. Usually, there are some solutions that one is making the cache of the translation bigger on the network adapter. A second is you use large pages. Instead of 4 kilobyte pages, you use 1 megabyte or whatever, gigabyte, 2 megabyte or gigabyte pages or so on. But yes, at some point you will run into the bottleneck of the actual pages. On some architectures like Blue Gene, it's a flat architecture, so there's no paging unless you use Linux or something. There's no actual paging that's happening, so that problem goes away in some sense.
So you mentioned that earlier a single core is not able to drive the network, while later you showed that most of the network protocol is moved actually to the network adapter. So would you elaborate more? What does it mean that a single core cannot drive the network?
Right. So both statements are true. So when the protocol processing was happening on the core, the single core could not drive the network adapter. After the protocol processing got moved to the network adapter, a single core still cannot drive a full network. Okay, even though the protocol processing is happening in hardware, the core still has to tell the network adapter, send a message. It has to give some information, like here is my buffer, here's the length of my buffer, whatnot. Okay, that's a very small amount of processing, but even that amount of processing a single core cannot handle for current generation network adapters. If you do the full network protocol stack, oh yeah, forget about it. You'll never be able to drive the network with the single core. Okay, so another way to think about it is if you had the full protocol stack in software, you needed 100 cores to drive the network. With the offloads, you can now do it with 10 cores. Yeah.